Good morning, everyone, and welcome to your Friday Happy Math Hour. Thank you for joining us again on this second week. Hopefully, you are all getting used to your classes, settling in, seeing how fun and enjoyable they are. So, again, thank you for joining us today. Um, so, today we're going to be covering functions, evaluating functions, domain, and the difference quotient. So, let's go ahead and get started. All right, so let's start with the definition of what a function is. Okay, so the function is a correlation between two quantities, okay, or two relationships. Okay, so what the relationship that we're going to be talking about here is the set of ordered pairs. Okay, so one of the things to consider when we're dealing with functions is we're going to be looking at their individual components. One of them is the domain and range of a function. And the domain, the way that I like to tell the students what domain is, the domain refers to all the x values that a function will take and give. Now, the range is the opposite. The range is all the y values that the function um, will take and give. Okay, so here is the formal definition of a function. Is a set of A to set B is a relationship that assigns to each x the set A exactly one element in set B. What does this mean? Okay, so the way I like to tell my students is that for every x value, uh, there exists only one y value in the graph. Okay, so that's basically what that formal definition means. So for instance, this example, find the domain and range of this given set, right? So we have ordered pairs here. We have 1, 2, 3, 4, 5, 6. Again, these are ordered pairs. Our first one refers to the x, the 2 is the y, the 3 is the x, the 4 is the y, the 5 is the x, and the 6 is the y, respectively. Yes? Okay, so if we want to find the domain, again, what we want to do is so you can better see this relationship here that each um, um, x value, okay, corresponds only to one value. Again, the x values are the domain, the y values are the range. So, for instance, if you look at figure one, okay, um, my domain would be the 1, 2, 3, just like on the um, the example here. If I wanted to find the domain of this range, okay, and the range, the domains would be 1, 3, 5, and again the range would be 2, 4, 6. Okay, so here, so you can better see it as pictures. Okay, um, if I look at B, the domain would be here 8, 7 to -4, and its range is its corresponding y values to these x values. So the range would be 5, 9, -3, and 5. Again, if I write B as an ordered pair, it would be 8, 5, 7, 9 to -3, -4, 5. Yes? If I look at example C here, um, um, this would not be a function because again, the the formal definition of a function means that every x value has to have its own y value. And if you noticed here on A and B, um, A it has corresponds to only one element in the set B. Okay, so again, A is a function, B is a function, but C, um, oh, sorry, this C is also a function, excuse me. Each element here refers to its own y. So we cannot repeat the x, right? The one that's not a function is D, right? This is not a function because here we're saying that x is sometimes -5, x is sometimes 8, and 8 is sometimes 7. This is what we cannot have, yes? So the first three are functions and our D is not a function, okay? All right, so more examples of functions determine whether each relationship is a function. So again, this is the one I already answered to on in the beginning. We're giving this set 1, 2, 3, 4, 5, 6 is a function. And as I mentioned to you, each individual x value, the 1, 3, and 5, correspond to its own y value, right? So we don't have any repeating x's. So then a again, a is a function, right? How about b? So we have 4, 0, 5, 10, 7, 8, 6, 10. I have individual x values, my inputs for the domain 4, 5, 7, 6, and then they all refer to its own individual y value. And again, um, like that example, even though 5 has a 10, you see two y values. This is okay. The ones that cannot repeat are my x's, okay? So if I would put them here as a grid, even though, again, the 5 and the 6 all have a y value of 10, this is it's their own x value with its y value, yes? So it is a function. But if we look at C here, we have -5 as the domains are -5, 1, 4, and 2. Okay, so these are all different. So these are all with respect to um, that we don't have any that repeats. So hence, um, this is a function. Yes. So function or not function. How about this one? We have our domains are -1, 2, 8, -1. Yes. So here right away we see that this is not going to be a function because we have two inputs that are the same value, two x values, a -1 with a y value of 9, and we have that -1 value again, but now with an answer of 3. Again, our domain cannot have two different answers for y. Yes, so again, this one is not a function because my domain repeats. Yes. All right. Now, one of the ways that we can visually test this concept that every x value has its own y value is by doing this imaginary vertical line test. And I say imaginary because you're going to be given a graph, and what the vertical line test says that if you put a ruler or a pencil and traverse your line vertically, okay, and if your pencil or imaginary line that you're traversing through the graph crosses the graph twice, then that means that every that at that x value we have two y values. Yes. So for instance, if I look at the first example here, I have this curved looking shape graph, and if I do an imaginary vertical line, I'm going to hit the graph at two spots. That's just telling me that at a certain x value, for I have two answers for y, which I cannot have. So that first example is not a function. Yes. So if you see here, this I am putting this my red line. Okay. It's crossing at 2 points, so hence it's not a function. Now, if I look at the second one here, if I do an imaginary vertical line for this one and I traverse it throughout the graph, if I just go from left to right, my imaginary line, or in this case, my red line, is only going to cross my graph at 1 point. So that means that every x value only has one y value. So hence, that second graph is a function. And of course, the last one, we can tell that is not a function because if I do my imaginary line or my vertical line test using this red line, you see that the line crosses my graph at 2 points. Hence, not every x value has only one y value. Okay, so again, this one's not a function. So this is a way to visually see right away on a graph if it's a function or not a function. All right, so now let's look at some of these. Determine whether each equation represents y as a function of x. Okay, so let's start with A. A is x plus 4y is equal to 8. Is this a function? Okay, so one way that we can do is um, graph it, right? And if we would graph it, do our imaginary vertical line test, and if our imaginary type line test passes, then it is a function. Or what we can do is we can solve it algebraically, right? So one way to do is if you look at, again, A, if we wanted to solve it algebraically, we want to first convert this equation. I like to say that they give it to me, this is a line, and I know it's a line, but maybe you don't. But I want to put it in slope-intercept form, and that means solving it for y. And this is going to allow me to help me graph it. Yes. So doing it algebraically, getting it into slope-intercept form, solving for y, I get y is equal to 2 minus x. Okay. So what that means, hopefully by now you've gone over slope. Okay, and its y-intercepts. So this equation has a y-intercept at 2, and its slope is -1, right? So slope is rise over run, but since my slope is negative, I'm going to go down 1, run 1, and it produces this line. Yes? So again, if I were to do my um, vertical line test, I would know its graph would pass at least one time. Okay? Now, if I were to solve the other one, I know it's not a line, but if I would solve for y on this one, it would allow me to graph, um, and I would see that it gives me this parabolic shape. Yes? So again, going back to the questions here. Oh, sorry, I'm skipping the slides here. There. So I know A and B are functions. But what about C? Okay, so C, here, I know that if I were to graph, sorry, keep moving. If I were to graph this, okay, this is going to produce, let me bring out my pen. If I do my rectangular coordinate system, this graph is going to be a graph like this, okay? My x-intercept is going to be at +4, but again, if I do my imaginary vertical line, let me change colors. Um, colors. Hmm, Cannot change my colors. Okay, here we go. There we go. Thank you. You see that I have my line crossed at 2 points. So hence C is not a function. And if I do D, again, D is, I know this one is a circle, and hopefully you've done circles already in your class. This is a circle with a radius 2, okay? So again, if I do my imaginary vertical line, my red line, thank you so much, I see that my graph crosses at 2 places. So hence, C and D are non-functions. A and B were, but C and D are not. Okay. All right. So evaluating functions. Okay. This is the easy one. Um, so let's do an example of evaluating a function. So a function, its syntax is this. This is the way we read this. F of x is equal to the square root of 3x minus 2. And we want to evaluate. And what evaluate means, we're going to evaluate the function for a given x value. So here on A, they're telling me that x is equal to 2. So what I'm going to do to evaluate is everywhere I see 2 in the expression, I'm going to plug in the 2 in there. I'm going to replace that x with that number. So let's go ahead and do that. So we have this function f of x is equal to the square root of 3x minus 2. There is an x there. I'm going to replace that with the number 2, and then I'm just going to go ahead and simplify or go ahead and do the procedure. 3 times 2 is 6. 6 minus 2 is 4, and the square root of 4 is 2. Okay, so this would be my answer. The x value, the domain, would be the 2, the input. The output, the range of this value 2, is going to be also 2. Okay, so let's do B. X is equal to A. Okay, again, I'm dealing with the same function. Everywhere I see X, I'm going to plug in A. Okay, so again, A is not a number, so when I multiply 3 times A, well, that's just 3A. 3A minus 2, these are two unlike terms. I cannot simplify anymore, so that is going to be my answer. My answer is just going to be the square root of 3A minus 2. Okay, let's go ahead and do C. So C is much better, right? I think it's more fun, right? So for x, it's not just a number. I have an expression. The expression that I want to put in for x is 6 plus h. Everywhere I see x, I'm going to put 6 plus h. Now it becomes a distribution process, right? I need to distribute this 3 to the 6 and to the h in order for me to simplify. So when I do that, 3 times 6 is 18. 3 times h is just 3h. I can get rid of the parentheses now, and I have the minus 2. Okay. Now I can combine two like terms. I have a constant of 18 and I have a constant of negative 2. So 18 minus 2 is 16, and I cannot combine these any further, so this would be my final answer. The input, 6 plus h, is going to produce the square root of 16 plus 3h. Okay? So this is how we evaluate functions. All right, now let's go ahead and evaluate this function. Now this one looks a little bit scary, but it really isn't. This is a function that we call a piecewise function. And the reason why we named that is because if you see here, it's one function, but it's made out of two different pieces, right? Or two other functions, okay? Hopefully you recognize that one of the pieces of this function is a line, and then this other function is something that has a square. Again, and later on in chapter 2, we'll dive into what these are called, right? But right now, this is a square function, okay? And one of the things of piecewise functions is that, yes, I like to call them Frankenstein. They're like two functions in one, but I don't want to look at the whole graph of the individual function. We put restrictions on them. I only want to look at a piece of that function. Okay, again, hence the name, piecewise function, right? So this values here that you see on the right, these are my restrictions on my domain. This means that all I want to look at of the x values are the values that are smaller than negative 1. And for the second equation, I want to look at all the values that are greater than or equal to negative 1. Okay, so that's what these values mean. So now they want us to evaluate a. I want to evaluate this function at negative 4. So again, for these questions, you are not going to get two answers. Even though you see two functions, this value is only going to be up here because of this restriction is only going to be applicable on one of the two. So what you say to yourself, first you go down the list, is negative 4 smaller than negative 1? And the answer is yes. Negative 4 is smaller than negative 1. Because if I would test it to the second one, negative 4 is not greater than or equal to negative 1. So this negative 4 only applies to this first function. So if I'm evaluating a, okay, I'm going to use the function, that first one, which is minus 2x minus 2. And again, now it's evaluating the function that we just covered. Everywhere I see x, I'm going to plug in that negative 4. Okay, so here we go. Negative 2 times the negative 4 is going to give me a positive 8 minus 2. 8 minus 2 is 6. So the answer for a, the function at negative 4, the y value or the range of that input is 6. Yes? Let's do B. Again, we do the same process. Which does negative, this input, negative 1, belong to? So we go, is negative 1 smaller than negative 1? No, they're the same. But so then that means it applies to the second one. Is negative 1 greater than or equal to negative 1? The answer is yes. So I know that negative 1 is only going to be applied to the second function. F of x is equal to x squared plus 2x minus 1. Again, everywhere I see x, I'm going to plug in negative 1. Okay, so here we go. We have negative 1 squared plus 2 times negative 1 minus 1. A negative 1 squared is a negative 1 times a negative 1. That gives me a positive 1. Positive 2 times a negative 1 gives me a negative 2, and then we have the minus 1. So 1 minus 2 is a negative 1. A negative 1 with a negative 1 gives me a negative 2. And this is my answer. This is the y value that corresponds to this x value or input negative 1 for this piecewise function. Let's go ahead and do the last one. Okay, I want to evaluate f of 1. 1 is greater than or equal to negative 1. So again, it applies to the second function again. F of x is equal to x squared plus 2x minus 1. Again, I'm going to evaluate by everywhere I see x, I'm going to plug in 1. All right, so we have 1 squared plus 2 times 1 minus 1. So 1 squared is 1. 2 times 1 is just 2 minus 1. 1 plus 2 is 3. 3 minus 1 is 2. So this is my output, or this is my y value when my x input value was 1, again, for this piecewise function. All right. Now let's look at more functions, and let's look at what's called the difference quotient. Okay, so this is the formula for the difference quotient. Okay, this is a definition that for those of you who are gonna go to higher math and do calculus, you'll use this a lot. But once you get to that class, we'll show you other shortcuts that will help you with the math. Okay, but for right now, this is the fundamental formula and process for um, this difference quotient. And the difference quotient says to evaluate, I like to say it's a three-step process. Okay. You see that for it's a fraction. And for the numerator, you're going to evaluate the function first by plugging in this expression, which we've already done and practiced. We got to plug in this x plus h. To that expression or function, we're going to subtract the original function to it. And then the last step is dividing by h. Okay, so the best way to see this is an example. And just one more thing to point out here, we always put this h cannot equal 0. Again, because we do have a fraction, our denominator can never be 0 because then we have an undefined expression. Yes, it's something that we cannot not do, right? All right. So this is an example like what you'll see in your homework. For f of x is equal to 3x plus 1, find the difference quotient, right? So they give you the function, and that's what I'm going to do. Okay, so let's go ahead and do it. I like to do it in pieces, okay? Break it into three parts, all right? So the first part is evaluating this f of x plus h. The second part is evaluating the f of x, which is just the function itself, and then plugging in, subtracting, and then dividing by h, okay? So let's go ahead and do it. All right, let's do the first part. Evaluating the function for this input value x plus h. Again, the function that they're giving me is 3x plus 1. I'm gonna, everywhere I see x, I'm gonna plug in this x plus h. Again, we have a distribution property, or to simplify, we distribute the 3 times x, and the 3 times the h. Okay, so when I do that, I get 3x plus 3h plus 1. Okay, and I've simplified. I cannot simplify any further. That was the only thing that I can do was distribute that 3, but these are three different terms. All right, so that's the first part. That's what's going to go here. The second part, again, is evaluating the f of x, which is really nothing to evaluate. It's just substitute. F of x is just the function that they're giving me, 3x plus 1. So I'm going to subtract that, okay, to that first part and then divide. Okay, so I'm plugging it into the function. So here we have the first one that was in blue. The f of x plus h is 3x plus 3h plus 1 minus, and this is very crucial. You see that on my second part, I have a binomial, right? So it's two terms here. So I have to use the parentheses because I know that I'm going to have to apply my distribution property again, okay? I need to distribute this negative to these two terms that are here. And again, then the last thing I'll do is divide by h. So let's go ahead and do that distribution. Let's get rid of the parentheses by distributing that minus sign. So a negative times a positive 3x is a negative 3x. A negative times a positive 1 is going to give me a negative 1. Okay, so now I want to simplify. Is there terms that I can combine? The answer would be yes, right? I have two like terms. I have a plus 1 and a minus 1. These are two constants. These are can combine. And then I also have two x terms, right? I have a 3x and a minus 3x. Those can combine. And when I combine them, they eliminate each other. They go away. They become 0. So I'm only left with the 3h over h. Okay. So now I do the division. Since I have one h at the top and one h at the bottom, both of these become 1, or you guys like to say they cancel, eliminate. So your final answer is going to be just 3. Yes. So again, easy stuff. This is applying what's called the difference quotient to a function. Okay. All right. Let's see. Let's do it one more time. Let's do one a little bit more challenging with a trinomial this time. Okay. So we have the given function x squared minus 4x plus 7. And again, they don't tell me, but I know that this is the formula for the difference quotient. They want me to find the difference quotient. So let's do it in pieces. Okay. So first, let's evaluate the function at x plus h. Everywhere I see x, I'm going to plug in this value x plus h. Now it's in two places, the x plus h squared minus the 4 times x plus h plus 7. Okay, so the first one I can expand the x plus h squared. That means that I have two of these guys. I have x plus h times x plus h. And then the second one, I just distributed the negative 4. Negative 4 times x is negative 4x. The negative 4 times h is a negative 4h. And then I have my constant, the plus 7. Okay, but what about this guy here, the one that x plus h times x plus h? What we can do is we can do FOIL, right? And that's just a bigger distribution. That means that this first term has to be distributed to the other two terms, and then the second term has to be distributed to the other two terms. So when I do this, x times x gives me the x squared, x times h is the xh, and then the second term, h times x is another xh, and h times h gives me the h squared. And then I have the stuff that I had before, the minus 4x, minus 4h, and the plus 7. Let me see. Can I simplify? Can I combine any like terms? Okay, so I do. I only have two like terms here. I have a xh and an xh, so I can combine those. So when I combine them, I get x squared plus 2xh plus h squared minus 4x minus 4h plus 7. That was the only thing that I can combine that one, right? So that was the first part. The second part, let's evaluate f of x. Again, this one's easy. The second part is just the function itself. Or I know Ms. Chuka likes to say, I'm replacing the x with x. But since there's already an x, hey, there it is. I've done it. I evaluated the second function by putting the x, but it's the original function, right? It's ex squared minus 4x plus 7. Third part, let's put everything together and simplify. Okay, so again, I have my blue and green, they're being subtracted from each other. But again, because I have a polynomial, I have a trinomial, I want to put parentheses because I have to distribute that negative sign, okay? And all of it is divided by h, okay? All right, so let's do that first. Let's get rid of the parentheses by distributing our negative. And when I do that, a negative times a positive x squared gives me that negative x squared. A negative times a negative 4x gives me a positive 4x. And a negative times a positive 7 gives me a negative 7. Okay? All right, got rid of my parentheses. Let's try to simplify. Can we combine like terms? The answer would be yes. Okay? Um, I have an x squared and an x and a minus x squared. Those get eliminated, become 0. Have a minus 4x and a plus 4x. Those become 0, so they got eliminated. Have a plus 7 and a minus 7. Those get eliminated. So I'm left with only minus 2xh plus h squared minus 4h. So the last part is to divide by this h. Okay, so one of the best ways that I like to think about how to divide is by factoring out the numerator. That way you can do what you guys like to do, right? Is once I factored out the common term from the top, which all three terms shared an h, I put it outside. I can easily now say that this h cancels with this other h that's at the bottom. But I know it doesn't cancel. H divided by h just becomes 1. But I know you guys like to say it cancels. And it leaves me with my answer. The answer for this problem is just minus 2x plus h minus 4. Okay, so for those of you, I like to always throw this as a test question. So make sure you study them because most of us like to throw this as a test question. So study it, okay? All right. So again, this will be my answer for this problem. So let's do domain, and I'm going to pass it over to my colleague, Ms. Chuka. Go for it, Ms. Chuka. Go ahead.
Right, cool. Thank you, Ruben. So let's look at domain. Domain is going to play an important role throughout the semester. And so for domain, we can look at, for example, a graph. So the domain is basically all the x values that are being used to make this graph. So for example, if I was to just pick any x value here, let me pick 5. If I go up, it's going to be part of this graph. So the domain is going to be everything that is used for the x values to create this function. And so one of the things I like to tell my students is think about the domain is going to have some restrictions, and they're going to appear anytime you have a fraction that has a denominator, has a variable in the denominator. So that's one thing to look out for. The other time that it's going to have restrictions is if you have a square root and if the radicand has a variable. So if you have that, then it'll have a restriction. And then in later on in the semester, we're going to cover something called logarithms. So if you have a logarithm, then there will also be restrictions. But if you don't have any of these three, then the domain is always negative infinity to positive infinity. So let's look at some examples. So for letter A, we have y equals x plus 5. So do you have any fractions that have a variable in the denominator? Well, here we don't have any fractions. Do we have any square roots? No, no square roots. And actually, it's not just square roots, it's any even root. Do we have logarithms? So a logarithm, you would see the word log, and we don't have that. Since I don't have that, then my domain is going to be negative infinity to positive infinity. So let me skip those. And so that would be our answer. Let's look at letter B. And if you look at the graph, this is a line, so that would also help you figure out that domain. So for letter B, do we have a fraction? No. Do we have any square roots? No. Do we have a logarithm? So the answer is no. Therefore, our domain is negative infinity to positive infinity. So here, if we were to graph it, it's a parabola, and we know that all these x values will be used. Even if I pick an x value all the way over here, and if I go up, it doesn't touch my graph right now, but the arrows tell me that this is going on forever. For letter C, oh, let me go back. Yeah, that one. So for this one, which is the next one, do we have any fractions? And the answer is yes, right? So we have a fraction with the variable as our denominator. So that should give us a red flag. We're going to have some restrictions. So to find those, we set the denominator equal to 0. And essentially, what you want to ask yourself is, what values of x will cause me to have a 0 in the denominator? Because we cannot divide by 0. So in this example, x equals 0 is going to be our restriction. And what that means is that you can use any number except for x equals 0. So what we're going to do is we want to write it in interval notation. So if we can use any number, that would be negative infinity all the way to 0. And then we're going to use this symbol, which represents union, and then from 0 to infinity. Let me just draw really quick something here. If I had a number line, let me get my pen. If I had a number line here, here is 0, and we can use everything here and everything here except for 0. So why do we even put the number 0 here? We have so many numbers that are close to 0 that we can't really identify them, right? So what we want to do is we write the number 0, but we use a parentheses to represent that we're really not using 0, but we're using all those extra little numbers that are close to 0. So anytime that you want to exclude something, we use parentheses. If you want to include it, then we use brackets, which we'll see in a little bit. So let's try another example. So I have an equation. I see a fraction. I have a variable in the denominator. So that should give us a red flag. That means we have some restrictions. So to find it, we can set x minus 6 equal to 0. Solve for x, so we get x equals 6. This tells me that the domain is going to be all real numbers except for 6. So we're going to go from negative infinity to 6. Notice I use a parenthesis because I don't want to include 6. And then union 6 to infinity. Okay, let's look at, these were the graphs here. That way you can see a visual. And let's go on to the next one. So y equals the square root of x. Since you have a square root, again, that gives us a red flag. We have restrictions. And so in the square root, you want to have only numbers that are positive or 0, so from 0 to infinity, because we can't take the square root of a negative number. So what we can do is we set the radicand equal to greater than or equal to 0, and then we solve for x. So here it tells you that the domain is going to start at 0 and go to infinity. So how do we write that in interval notation? It's going to go from 0 to infinity. But notice that now I do use a bracket because I can use the number 0. If we had, for the next one, we take our radicand, x plus 5 is greater than or equal to 0. We're going to go ahead and subtract 5. And so this tells me that the domain is going to start at negative 5 and go to infinity. And if you were looking at the graphs, we can see that the graph starts at 0 and goes to infinity. So all these negative numbers on the left side of 0 are not going to be used to make this graph. And then the same thing here. We start at negative 5 and it goes to infinity. Okay, so now let's look at it a little bit different. What if I had a graph like this? So it says use the graph to find the domain and the range, and then we're going to continue there. So when we have the domain and range, then we can look at, for the domain, what are these x values that are being used? And so if I was to just pick an x value, let's say 5 here, if I go up or if I go down, it's not going to touch my graph. And I know this graph is not continuing because it doesn't have any arrows, right? So the smallest x value here is going to be at this point. And then the largest x value that we use is going to be at this point. So notice here that this point here is an open circle and this one is closed. If you have an open circle, that means that the point is not included in the domain. If it's a closed circle, then the point is included. So open circle, that means we'll use parentheses. Closed circle, that means we use a bracket. And when you're writing the domain, you always want to write your smallest number first. So we have negative 2, and then we have a positive 2. So that means that only the values between negative 2 and 2 are going to be part of your domain. Now for the range, you want to ask yourself what is the smallest y value that's being used. And this point here looks like negative 4. And the largest y value is at 5. So my domain will be from negative 4 to positive 5. Domain will be from negative 4 to positive 5. If we want to evaluate this function at f of negative 1, so remember that negative 1 is what replaces your x value. That's your x value. So we go to our graph. Here is negative 1. And then you want to see what the y value is. So if you go up, there's nothing here. But if we go down, then we land at this part of the graph. And this value is negative 4. So f of negative 1, if we go down, will give us negative 4. F of 0 is right here. And if I go down to my graph, then that's going to give me a negative 3. And then for f of 1, which is right here, if it goes down, it looks like negative 4 again. And then the last one, f of 2, if I go up to my graph, will give me 5. Okay, let's try another one. So here, let's find the domain. So notice here in this graph, if I look at the left side of my x values, I have an arrow. So that means that the graph goes on forever. So my domain is going to be all these negative values. And then it's going to go all the way over here. And I have an arrow. So that means that my domain is going to continue for negative infinity to positive infinity. What about the range? The range, it starts here at negative 2. It has an open circle. That means that negative 2 is not included. Therefore, we use a parentheses. And then if we go up on the y, we can see that the graph is increasing. It's going to keep going up. So that's going to be to infinity. F of 2 is right here. So at f of 2, what is my y value? well, my y value is just 0, which is right here. And then f of 1, well, f of 1 is either 0 or -2, but we know it's going to be 0 because that's where the closed dot is, right? So f of 1 is 0. And then f of 3, if we go up, then we get to 2. And then f of -1, if we go up, we get to 2 as well. So here we have determine the open intervals. And so now we're going to switch into increasing, decreasing functions. And I believe Mr. Isasi is going to cover increasing, decreasing, and constant functions.
Thank you, Yvette. Hey, students. I mean, for these, they're going to be the intervals where the function is increasing, decreasing, or constant. So, for example, here, if we notice, I mean, the function is coming from the left side, which is from -infinity, and it's coming down. It's going to reach the 6. Here, guys, I mean, for these intervals, it's always the domain. I mean, the x values. Okay. So here, let me see. Let's go to the next slide. You see, it's decreasing. Okay, and it's going to go from -infinity all the way to +6, right? Because the intervals is only the x values, right? So it's going to go from -infinity to 6. Okay, let me see here. And then it's increasing from 6 to +infinity, right? Because it's increasing from the 6 here, from the 6, and it's going up all the way to infinity. So it's going to be from 6 to infinity is going to be increasing. And for the constant, there's no constant because when it's constant, it's like a horizontal line. So here are the results for this function of x squared minus 12x. It's increasing from 6 to infinity. And it's always parentheses, guys. You never put, we never put brackets. And it's decreasing from -infinity to 6. And for constant, it does not exist. Okay, let's try another one here. If you notice, this function is f of x equals to the square root of x squared minus 25. So we have to find the intervals of increasing, decreasing, and constant. Now again, if we notice, coming from the left to the right, it's decreasing from -infinity, and it stops here at -5. And it's increasing from 5 all the way to +infinity. So the intervals of increasing will be from 5 to infinity, and decreasing will be from -infinity to -5. And for the constant, again, as the previous function, there's no constant, so the constant does not exist. Now we're doing finding the intercepts, the zeros and intercepts and solutions and also roots. They all mean the same thing. In this case, right, they're saying to find the zeros, which are the x-intercepts, which means, right, where does a graph cross the x-intercepts? Here we have 3 different graphs here. Okay, so these here, guys, are my intercepts, the -2, 0 for graph number 1. And also this is like, let's see, this is 1, this is 2, like this supposed, well, this is 5/3, right? But I guess when you graph it in the calculator, guys, you can get this, or you can get them by factoring. But it says here that this is 5/3 and this is 0. And now here, right, because this one here, guys, I mean, graph number 1, it's a little bit, hard to say, right, because it's between 1 and 2, and it's a little bit more than half. But this can be only done by using a calculator, guys, when you graph it, or by factoring the function 3x squared plus x minus 10. And on the graph number 2 in the middle, we notice this is the square root of -10, and this is positive square root of 10. By the eye, we cannot see that. But again, we can do it by doing it algebraically or by plugging in the calculator. And the one here on the last one, right, we have h of t equals to 2t minus 3 and t plus 5. So this is a graph, but we're looking for the zeros, which would be 3 over 2, 3/2, 0. Now they want us to find the zeros algebraically. Again, with the graph, it's a little bit harder, guys, because at times, if it doesn't go exactly to an integer, right at what is that, If it's between two numbers, then it's going to be hard, to find them with a graph because it's hard to tell what it is. But algebraically, you cannot go wrong. Okay, so these are four functions that we're going to find the zeros or the x-intercepts. Let's start with function number one. Okay, now guys, so to find the x-intercepts, the rules are we let y equals to 0 and we solve for x. So in this case, right, we have y is 0, f of x, right, is a function which is the same thing as y equals to 3x plus 18. So we're going to substitute 0 for the f of x. So here, guys, what we did here, they subtracted 18 from both sides. And then they divide by 3. So negative 18 divided by 3 will give us negative 6. So the negative 6 is my x-intercept or my 0. For the second function, right, again, we let f of x equal to 0. We have the root of 3x plus 2. So to eliminate the square root, right, because it's a square root, it's a 2, right, so we square both sides. So if we square the left side, 0 squared will give us 0. If we square the right side, the square root and the square, will be 1. So that's why, or they go away, right? The square root cancels. The square root cancels the square, so there'll be 3x plus 2. So we have 0 equals to 3x plus 2. We subtract 2 to both sides. So we give us negative 2 equals to 3x, and then we divide by 3. So it's going to give us negative 2/3 equals to x. Now on the third one here, on the corner to the left. Okay, for this one, guys, I tell my students, right, this is my numerator, that's the x plus 3, and the bottom part is my denominator. So at times, this is a little bit challenging, guys, for students. Okay, but what I tell my students is that you always let the numerator equal to 0 and you solve for x. And this is the reason why. Let me go here. You see, guys, right? Because I want to get rid of the 2x squared minus 6. So I'm going to multiply both sides by 2x minus 6, right? By 2x squared minus 6. If I multiply 2x squared minus 6 on the right side, it will cancel with the 2x squared minus 6 on the bottom. So that's equal to 1. That's why we're only left with x plus 3. If we multiply 2x squared minus 6 times 0, it will give us a 0. And remember, when I mentioned, guys, that the observation here is that you always let, when you have like a rational function, you always let, right, f of x equal to 0, and then all you do is let the numerator, which is the x plus 3 equal to 0, and you eliminate all this work that we just did. So if you follow this observation, you're going to let the numerator equal to 0, and we have 0 equals to x plus 3. We subtract 3 to both sides, so we have negative 3 equals to x. So that's my 0. Now the one on the right side, okay, we let it equal to 0. So here we're going to ask yourself, we get 0 equals to negative 81x to the 4th plus 9x squared. Here we factor out an x squared, but eventually we could have factored out a 9x squared. But here, I decided to just factor out the x squared. So if I do that, I'm going to get x squared equals to negative 81x squared plus 9. And you can always check your work, because if you distribute the x squared times the negative 81x squared, it will give us negative 81x to the 4th. If I distribute the x squared with a 9, it's going to give us 9x squared. So I know this is that I did factor the greatest common factor out. Now we said both equal to 0. 0 equals to x squared, and 0 equals to negative 81x squared plus 9. So on the left side, we just have 0. That's one of my zeros will just be 0. On the right side, we subtracted 9 to both sides. Subtract 9, right? And then we divide both sides by negative 81. That's where we have negative 9 over 81. Negative 81 equals to x squared. Then we take the square root. When you take the square root, this is the same thing as 1 over 9, which will be the same thing as plus or minus 1/3. So for this one, guys, it's going to have 3 roots, right? X equals to 0, and x equals to plus or minus 1/3. Okay, now even in odd functions, function y, which is equals to f of x is even for each x in the domain of f, if you're going to substitute negative x for every x in the function, and if you get the original function, it's going to be an even function. And we do the same thing, right? To test it for odd functions, we're going to substitute the negative x negative x for every x in the function, and then we could factor out a negative and we get the original, is going to be an odd function. So here are two examples. Example A, we have x squared, f of x equals to x squared plus x. And B, we have g of x equals to x cubed plus x. Okay, so here on A, right, we're going to plug in negative x for the x on x to the fourth, and also on the x for x squared. So we do that, is going to give us parentheses negative x close parentheses to the fourth power plus parentheses negative x close parentheses squared. I tell my students that every time that you're going to evaluate a function, that you always put what you're plugging in with parentheses. This way you eliminate the mistakes with a negative number. So if you notice, we have let me see if I can write here. We have x to the fourth plus x squared, right? Because negative x to the fourth power will give us x fourth. Negative x to the squared power will give us back x squared. In other words, a negative to the even power will be the same. Will be will be a x, and a negative. Every time that you raise a power to the even, you're going to get the original. So if you notice here, guys, we have the original, right? That means the function is even. So A will be even. Now look at B. We're going to plug in negative x there, right? And also there. So then we get negative x cubed plus negative x. If you notice, this here, guys, is not the original, right? So that means that is not even. So what we do, we're going to factor out a negative x. You see, that's what I did here. Factor out the negative x. Okay, I'm going to go from here to here. I factor out the negative x, and then I get the original. You see, we have negative x, and I got the original, which means this is going to be an odd function. Okay, now, here, here we have another one, right? We have f of x equals to x squared plus 5. So again, I'm going to plug in the negative x in there, which I just did here, right? And like before, if we have a negative x, right, to the even power, is going to give us a positive. If we notice, this goes back to the original, right? That means the function is even. Now look at B. F of x equals to x cubed plus 6. Again, I'm going to plug in the negative x there for the x on the x cubed. And any negative, right, to the odd power, will give you negative. So here, guys, here we're going to get negative x cubed plus 6. If we notice, this is not the original. And if I try to factor a negative x, a negative number, is going to give us x cubed. I'm going to try to receive right here. It's going to give us x cubed minus 6. You see, guys, this is not the original. You see, so it's also it's not going to be neither even nor odd. Now, here's a summation here, guys, okay? Here's like an observation. If all the exponents are even, right, the exponents are even, then the function will be even. If all the exponents are odd, then the function will be odd. Now, how about with a constant? If all the exponents are even and a constant is present, the function is even, okay? With a constant and they're even, the function will be even. But here, guys, I did a mistake here, guys. If all exponents are odd and a constant, right, with a constant is present, then the function, I did a mistake here, guys, it will be neither. Okay, so for this one, if you have all odd function, all odd exponents with a constant is present, the function will be neither. Okay, let's put an N for neither. And then if you have mixed even and odd exponents, the function will also be neither. Okay, so I apologize for the mistake here, guys. So that's why I already corrected it. Okay, and I believe that's it for today's presentation, and I'll send it back to the host.
Thank you so much, Ms. Ivachuka, Mr. Ruben Carizales, and Mr. Albert Isasis for your wonderful presentation. If you would like to download a copy of the presentation, you can go up to the right top corner of the screen and click on the box with the arrow going down while the presentation is still on the screen. We want to remind you all about our previously recorded sessions, which are available to you on YouTube at the Tejano Virtual Events playlist. This session will also be available on this playlist later today. Also, linked is a short survey to help us improve our Tejano virtual event sessions. Please take a few moments to fill out that survey. Before you leave, we want to share the Tejano virtual events flyer with the sessions that we will have next week. At 1 p.m. today, we will have the computer lab, the ISC, and the bookstore making a presentation for you. And we'll be back with Happy Math Hour next week at 11 a.m., where in Math 1314 and Math 1324, we will be covering factoring. So come and review all the different factoring methods. Thank you all for coming in today. We hope that you all have a lovely weekend. If you have any questions, please feel free to use the chat box or the mic. We hope to see you again next week with our next Happy Math Hour. Thank you.